And welcome, ladies and gentlemen, back to PASCO Laboratories. It's so nice to have you here with us today. I am JP, and you're probably wondering this week, what does the P stand for? Well, I'll give you a hint. That's right, the P stands for pressure. And what are you thinking? Pressure? I'm talking about waves, and I'm talking about pressure like oscillating pressure waves. And oscillating pressure waves, we know, is sound. And that's what we're going to be talking about today, because we had a very wonderful email that came in from Miss Carpaga all the way out in the United Arab Emirates. This is Miss Carpaga here, by the way, sends in a picture of her family. We're happy to have her with us. It's 11 p.m. and she joins us every week for PASCO Live, but she asked this very simple question. JP, if a tree fell in the forest and nobody was there to hear it, how fast would the sound travel? Well, Miss Carpaga, we're going to answer that question and so many more, because today we have with us Miss Ann Hanks and Mr. Brett Sackett, who are going to demonstrate everything about sound, things that you've never seen before, probably things you never even thought were possible. Ann and Brett are going to show you. So let me bring in Ann, let me bring in Brett, and let me turn this awesome opportunity to explore sound to the Ann and Brett Show.
Hello.
Hey, JP.
My lovely assistant.
Being of sound mind and sound body, I'm the perfect person for this.
And you're going to keep your mask on.
Oh, I can take it off.
Yeah.
If you like.
We're safe. We've got
We
a
are
division.
safe.
So today we have our resonance air column here. And it has a plunger in it. Can you move the plunger
Yeah,
for
here's
me?
the plunger.
Yeah. So it's moving back and forth there.
And this plunger acts as a barrier
Yeah.
for the sound to reflect off of.
So this is the open end of the tube, and we have a closed end of the tube, so we call this a closed tube. And I just want to demonstrate what happens when I put a tuning fork up to it. Keep going. Here. There, move it to that spot. We have these little sliders that allow us to mark where the nodes are.
And you can hear the amplitude
Go all the
increase
way up, then.
when we hit a node. Because that's the point.
I think you're hitting it. You might be hitting an overtone there. Just slide all the way to the end and then back up. There it is.
There it is, okay.
Okay. So this is when it's in this position, there's one node here and one antinode at the opening. And there is a little end effect that we won't worry about right now. Then when he slides it back further, he's to the point where there is another node, and there's a node here and a node here, so you're actually hearing the harmonic of it. Now, let's switch over and use a little electronics. I have an 850, and you can also do this with a 550, but today we're going to use the 850. I've got a speaker hooked up to the output of the 850 so that I can control what sound. This gives me a much more reliable tuning fork because I don't have to keep hitting it to make it sound. Get rid of that. And then I've got a sound sensor hooked up. This is a sound sensor, and I'm just going to place it out here in front so that it can hear when there's a resonance.
Right. And this sound sensor is one of our analog sound sensors, which is different from a wireless sound sensor we sell. And the reason we use this is that we can sample much faster, and we can just get a lot better real-time data collection of the changes in sound pressure levels.
So what I'm going to do is move these so that I can find the nodes for this particular sound. And we're going to make it be at 600 hertz. So if you look at the FFT of the sound sensor, you can tell when it gets louder. You can see here. Oh, there, it got pretty loud there.
Right.
Where's that?
Yeah, so when I move the piston back and forth through the node, you can hear the amplitude increase, and that's how you can find where the node is.
Yeah.
Finding that point where the amplitude is highest.
Okay, so keep going. Let's find the other one.
And there's another one.
Out there? Yeah. Keep going. Okay, so we can keep going and getting more, but there's the last one. Go ahead, take it.
Right there.
So now you can see that there's a node here and an antinode here, which is a quarter wavelength of the sound. From node to node, it's half a wavelength. So this, from node, and skipping one, you have two nodes separated out here. That's a whole wavelength. And I'm going to just measure that to see how long the wavelength is. And you are getting a look here at a very special meter stick because although we're not selling this meter stick yet, we will be soon. And it'll be the subject of a later PASCO Live.
Yes, indeed.
Because we're going to do everything you can do with a meter stick. This meter stick is aluminum and hollow, and it's got some pretty special things you can do with it besides just measure directly. So this is reading off here. I'm really reading this at an angle. It looks like 50. Let's see, I've got this on 2, so 57.5. So if I put in the wavelength of this in meters, it's 0.575, and I have the speed of sound is equal to the wavelength times the frequency, and then we know the frequency because we measured it and also because we told it to output 600 hertz. So 600 hertz times 0.575 meters is 345. Let me just slip the temperature sensor into the tube. This temperature sensor is plugged in to one of the passport ports on the 850, and it's reading 301 degrees Kelvin. Yeah, if you don't know what that means in Celsius, there's Celsius.
It's a little warm in here.
It's a little warm in here, yeah, it is.
It's all these lights.
But it's nice to be able to just change the units, because when you apply this to the equation that for the sound as a function of temperature, you have to have the temperature in absolute degrees. It can't be in Celsius. So putting that 301 into the equation gives us 348 meters per second. And I'm using the calculator in Capstone to do that calculation. So those are quite close together. Of course, I only made one measurement. Normally you would measure every single node and you'd get a little bit more data and know what your uncertainty is.
Yep.
And Brett, we've got a question coming in, and I don't know if you can answer, but Jim is asking, what does a sound wave look like in 3 dimensions?
Depends on where it's coming from. We have a pretty small speaker here. It tends to put out in quite at like a point source, but it is somewhat directed. So in this case, we're actually getting quite a bit of sound planes of waves coming out of the speaker. It's So it would look like a kind of curved plane front as you go away from the speaker. And we're just sampling a little piece of that down the tube.
Mm-hmm.
Now, I want you to put this back at this resonance point.
Okay.
And this sound sensor is special in another way. It has an external mic, which is right at the end of this rod. And I'm going to plug the external mic into the sound sensor. There we go. So now I'm reading the sound from this mic rather than from the microphone at the front of the sound sensor. And I'm just going to slide this down the tube so that I can sample what the sound level is inside the tube. So we're set it at a resonance, and let's just look at this again. Here's the FFT, kind of loud there. Okay. And then as I slide it back, oops, sorry. See, here I'm at an antinode, and so I'm picking up a little bit of the speaker itself, but it's quiet inside the tube. And then when I get to another node, it gets the amplitude of the FFT goes up. We're not hearing that change because we didn't move the piston.
Right.
And so here it goes down again, and then it'll go back up again when I hit the next node. So you can see that the sound wave is in the tube, and we're sampling the nodes as we go down the tube.
And that's a good way to compare where the nodes are, whether the piston is at that point or not.
Right. So let me go back to using the other microphone on here. Just put that back out here.
And the sound labs are like one of the best lab days in physics when you've got 8 or 10 or 12 lab stations
Yes.
all doing
And if you're all doing
signal
it,
generation.
you need to have your students choose different tuning forks or different frequencies. Otherwise, you can't tell when it's your tube going, resonating or not. So the next thing I want to do is an open tube.
So let's make it an open tube.
Yeah.
We'll get rid of the piston. Now it's open at both ends.
Yeah. And it should have a fundamental frequency when there's only one node right in the middle. So let's just take these off for a second. Would you take, no, leave that one.
That one? Okay.
So if we have one node in the middle and an antinode here and an antinode down there,
Because it's open at both ends.
because it's
So we get an
now
antinode.
open at both ends, although the 550 is in the way, you would have the fundamental frequency for the open tube. Now this is where tuning forks fail you, because I don't have a tuning fork that happens to be that particular frequency. But I can figure out what the frequency should be, and I can apply it with the speaker. So if I just know the length of the tube, would you mark that and then move that down? You're gonna need the other end here.
Okay.
Was it 121?
That's about, I'm getting about 120. I'm getting about 20.
120? Okay.
Assuming my finger was super accurate.
So let me just take my calculator, and I'm going to say that the speed of sound was what in here?
Was it 348 earlier? Or
Yeah, well, it was 348.
I think it was 348.
Okay, so we have the speed of sound is 348, and if we divide that by the wavelength, and in this case, this is half a wavelength. You said it was 120.
I measured 20 centimeters from
Yeah,
the end there,
so
to my
it's
thumb.
120. So this whole length here is half a wavelength of the sound. So we double that, it's 240 is the wavelength of the fundamental. So that's a low note.
That's a low note.
Yeah. So I'm going to divide by 2.4 meters into the speed of sound. and that gives me 145. So 145 is the fundamental note on this tube. Now, this little tiny speaker tends to make better sounds at higher frequencies because it's a small speaker. So I imagine it's not going to do too well at 145, but we can try it. Turn the signal generator on here. Just switch. I'm going to switch to a different setup here. Open tube. Okay, so in this particular program, I've taken advantage of PASCO's new Blockly coding that's in Capstone. It's actually in, you just click on the code button, it opens up, and you can code in Blockly. And I'm using that to control the 850. And I can tell it then, in this case, I'm going to put in the fundamental frequencies 145, 145, and then what the short little program does here is it just doubles that to 290 and doubles it again, or triples it. And so when it doubles it, I end up with where's my little clips?
Here's a clip.
Then you end up with a harmonic.
The other ones are right there.
Where you have something that looks like about like that. And so you get to explore the fact that for the open tube, you're looking at different harmonics, and it steps through them automatically. So listen. So let me put this out here, and then you can hear what it sounds like when I'm not in front of the tube. Now this, when I put it over here, now it's going to resonate. So you can hear that it is louder. And of course, you can just fiddle with the frequency around one of those to hear it get loud and quiet. This is a little bit like our sound tubes that we sell, where you have this is an open tube as well.
Yep.
And you can use the sound sensor to detect that sound and try to go really slow to get the fundamental. If you're musical, you realize that wasn't the fundamental. And that's what you find out when you actually measure through the 850, because that it's not doubling it. And so the reason is you're not hearing it, the fundamental, is because if I go slow enough to do the fundamental, it doesn't sound. It has to go fast enough to get enough air going through it to make the sound. And so that's actually the lowest note that I can get with it, but it's really the first harmonic. And so then that's the second harmonic, third, and you can find that out by measuring it with the sound sensor. Okay, so now let's go back to closed tube.
All right. There we go.
And I want to do, let's see. This is something that I had never done before until I started to mess with this. a couple days ago just to see what we could do. I wanted to make two sounds at the same time and put it down the tube. And so it turns out you can do that, but I need to have two different speakers. So I have a signal generator. Now I could have used the 550 for this, but I really wanted to show off the signal generator.
There's a lot of love for the signal generator.
Yeah.
It's a PASCO classic.
Yeah, it is. And of course, it can be manually run by the buttons on the front of it. And it's a great signal generator because it puts out a lot of power. And I'm going to use it to generate a 1,000 hertz signal to this speaker. And I'll generate the old 600 hertz to the other one. But the other thing that's cool about this function generator is that if I hook it up to my laptop through the USB from the back port here, I can control it through Capstone. So let me see. I do not want to add my temperature sensor here. So no. Okay. So here I now have in my hardware setup here, you can see the interesting, it's confused over which sound sensor I've got. I'm going to delete that one. Here, put the right sound sensor on here. There we go. So I have both the function generator hooked up and the 850's function generator. And then I can control both of these. I put the 850 output on 600 hertz. I put the function generator on 1,000 hertz. And yep, it's on 1,000 hertz. So let's put both speakers up here. And I'm just going to angle them in to the tube so that they both are sounding into the tube a little bit. And let's see what we get here. Oh, I forgot my mouse. Oh,
There we go.
but
I can hear that.
I'm not seeing it on the FFT. Oh, there it is.
There you go. Yeah, I can hear two pitches.
Yeah. Now, it's not at resonance, so back it up. Yeah, there's a loud one right there.
Okay, there's one. One of the frequencies is right there.
Okay. Keep going back.
There's one.
This
There's
should
the
be
higher
the
one.
600.
I think, is that the higher one? That's the higher one.
I can't hear from here. All I can hear is what the speakers are putting out. Yeah, that is the higher one. I look
Yeah.
over on the FFT and can see it.
You can always trust the FFT. Are they both starting about the same amplitude?
I've got the amplitude of the 600 down pretty far. Let me go up 1 volt. Here's a little louder. Okay, go ahead.
There's definitely one there.
That's the 600.
There's the higher.
Keep going.
Okay, so here's right there.
Now, just go back to this spot. Okay, let me just disconnect one of these.
Yep, that's one right there.
Yeah.
That's definitely one.
That's the 600.
Yep.
And now,
So that's the same spot for both waves.
Yeah.
So both frequencies have a node that lines up around here.
and so they both sound right there. Probably takes a musician to hear it.
Turn that a bit more. There you go. Yeah, there you can hear both frequencies reflecting.
Yeah. So for one of those frequencies, it's actually got a node, one node here, and for the other frequency, it's got two nodes. So we're getting a 3/4 wavelength of the lower frequency, and then we're getting 1 1/4 wavelengths of the higher frequency.
Because right here, you can hear that's the lower frequency,
Yeah.
right? That's that one. And then here's the higher frequency.
Yeah. And the higher
And then-
frequency also sounds here.
Yeah, we can go back over here. That's the higher frequency also.
Yeah.
And then here, it's both of them. That's awesome.
Okay.
Love physics, right?
Yeah.
That's good physics right there.
Thank goodness for FFTs.
We love FFTs. You can always trust your FFT.
We're seeing some good stuff there, guys. And we've got a question coming in from our good friend Leonardo.
Let me turn this
As
off.
soon as you turn that off.
What?
Yeah, what did you say? We have a good question coming in from our friend Leonardo down in Florida, and he's asking, could you please suggest a good experiment about sound wave interference using 2 loudspeakers and 2 signal generators? Maybe outputs 2 and 3 of the 850 interface?
Okay. So outputs 2 and 3 don't have the current that you need for a speaker.
Correct.
That's why I'm using 2 different high current outputs here. So you would want to have 2 850s or a 550, 850, and then run each speaker, and you can place them like this, and then you can walk around the room. And what I did with my students was I actually took them outside onto the lawn and gave them a bunch of pencils and told them, wherever you hear it really loud, stick a pencil in the ground. And then they did that, and you get this radiating pattern of all these constructive interference points.
That's awesome. I like that idea.
Yeah, it works really well.
Yes, the outputs 2 and 3 on the 850 are for mostly for
Electronics.
high speed circuits where you have high frequency and low current. You could take those through an external amplifier if you wanted to, but what we've done here is we've used an 850 and then another function generator to drive these speakers.
So, if there aren't any other questions, my lovely assistant will clean up, right?
Well, thank you, Ann. Absolutely. I always clean up after Ann. JP, would you like to come back?
Sure, yeah,
Thank you.
absolutely. Thank you, Brett, and thank you everybody for watching what both Ann and Brett did here. Of course, we answered Carpaga's question, if the tree fell in a forest. We actually measured the sound, and we know now if you're in the forest and you've got 2 loudspeakers, you can actually put a pencil in the ground where you find those nodes and you find both constructive interference, and I'd love to see that done. So Ms. Carpaga, when you do this, please send in pictures, and for any of you, if you send in your pictures or your questions, we use them here on Facebook Live. We've got a special gift for you. And speaking of a special gift for you, I know you are all wondering, what is today's PASCO FOMO going back to SCOMO promo? And of course we do have one, as we have one every week, and it has to do with all the equipment that you see here. You see the 550, you see the 850, you see all this great equipment here, and we have that special word today is pressure, oscillating waves of pressure. And if you say pressure in your email to Isaac Martin, he's ready to give you a great deal on this great higher education equipment that is available to you so that you can start doing demonstrations with your students today, start showing these things to your students at home, and when they come back or are in your classroom, you can start doing all these great sound experiments. So reach out to Isaac Martin, not to be confused with Blue Martin, and let him know that you're very interested in this equipment. Today's word, pressure. And for that, ladies and gentlemen, we hope you enjoyed everything that we offered to you here at PASCO Live at the PASCO Laboratories. And Ann, Brett, and I are all wishing you the best of luck, great teaching, and good day.